Okay, it's 1 o'clock. Welcome everybody to our next HDF clinic. Yeah, I just checked the sign-up sheet again. There weren't any questions there, but I'm going to pause nevertheless for those of you who are here. Are there any questions at the moment? No? Okay, we'll if there are questions, we'll keep coming back to that. Okay, let's dive right in. Last week's highlights. There were, in the announcement category, there were 3. Number 1, for those of you who missed the webinar last week about the Hermes project, the recording is available now on YouTube. And so I put the link here if you want to catch up on that. Feel free to do so. Number 2, there is a fantastic new blog post by John Reedy about the different cloud storage options for HDF5. He did an interesting sort of comparison between sort of S3-based file systems. The kind of he was assessing mostly read performance in this blog post, and yeah, he was comparing SSDs, HDDs, EBS volumes, HSDs, of course, in different build-outs, FlexFS, S3 Backer, S3FS, and so forth. So really, cloud storage options, the title says it, and then the kind of performance that you get with these different options. Very interesting, highly recommended. And then we have another upcoming. Scott just did a training session a few weeks ago, and that's online, but there's going to be another one at Argonne coming up in late August. And yeah, I put the link here. You can sign up. It's free. There are, if you are abroad, there are some restrictions for foreign nationals. You can check what those restrictions are. But by and large, yeah, it's free, and unless you fall into this category, then that might be a little difficult. But yeah, check it out, and it's going to be a great event. And it's also going to be the last event, if I remember correctly, was about an hour and a half. So it was a lot of material to cram into a relatively short time. Oh. There is a question here. Where are the links? Can you see my screen? They are sort of, if I hover my mouse here over, here's one of the links, for example, for this workshop. If I go there, this is what that looks like. Does that make sense? Okay, but you guys can see my screen, right?
Yes.
Yes, great, good. Yeah, so the links are in the notes here. Yes, and then you might ask, well, where are the notes? Sorry, they are just in the usual place. So here's where the notes are. Right. Oh, thanks. Yeah, somebody posted them. Thank you. All right. So links are here. Yeah. So Scott, the last webinar he did, I think that was sort of for a broader audience. I think that was an hour and a half to 2 hours. This is a longer event, and it's mostly for intermediate and advanced users. But yeah, there is going to be a lot of time for asking questions and covering a lot of new features in depth. And so it's going to be a great event. Okay, before I continue, are there any questions at this point? No? Okay. Keeping going here, lots of things happening on the forum. Again, my very biased selection here. There is a thread about the progress of this backport of the H5D chunk iter function to 112 and 110, and it's sort of spearheaded by Mark. And I think, yeah, all I can say is it's a great community effort, and let's do more of this. Let's find ways of getting more community members involved in contributing to the library, as scary as that may sound on the surface. But again, the library, there are sort of obscure corners, but then there are sort of well-trodden paths and so forth. So as with any piece of software, there are, and even if it's just with helping improve the quality of the documentation, so there aren't only coding tasks as far as the library is concerned. There are so many other ways in which people can contribute, and it's great to see that somebody goes all the way and yeah, submits a PR for a backported function, and that's very welcome. Great. The next one is there, Mike Jackson, I believe, started this discussion around file-backed array, and he sort of provides a sort of pseudo code here. So the idea was, and this is also that came up at one of last year's Hug events, where I think Werner Benger was asking, well, couldn't we have an H5D read or H5D write call where rather than asking the user to provide a buffer, instead of having a pre-allocated buffer, basically have memory mapped data sets, so to speak, or memory mapped parts of an HDF5 file, more broadly speaking. And this sort of harps on that same idea. And so far, this question has gotten two interesting responses. One from Stephen, who has done a similar development in H5CPP, but also Rick, who is sort of the brains behind HDFQL. And he sort of gave us also a little bit of a peek or preview of what he calls sliding cursors that are coming in HDFQL, that at least as far as this, he provided an example for reading. Obviously, the pseudocode that Mike provided here is more of a write example. Nevertheless, so in HDFQL, the next version, I think that's what Rick was saying, is you have this concept of a sliding cursor or a sliding window, if you want to call it that. And yeah, HDFQL will take care of sort of bringing in new data when you reach the end of a selection. There might be chunks underneath, but not necessarily. And so that's very interesting to see. And I just copied, this is the example Rick provided, sort of a before and after. You can do this with the existing HDFQL. It's just a little more manual labor, so to speak, and the code is not quite as short. But with the new version of HDFQL, it's going to be very transparent, very user-friendly, I think is the right word. Okay. And then there was a third thread here. There's an extra, I apologize, an extra underscore that doesn't belong here. Yeah, somebody was asking, yes, you can use for many of the filters in some cases provided custom function H5P set deflate, H5P set this or that. But in some cases, these high-level wrappers, call them that, do not exist. And then you have to sort of take a little bit the pedestrian approach, the H5P set filter function. And then there are these CD values, these parameters, and the user's question was about, well, number one, how do I discover if a given filter that I would like to use has any of these CD values, or if there aren't any, and pretty much everything is hardwired. And so I believe my colleague Alan responded, and he said definitely a good starting point is to start with the, call it the filter registry, where users register their filters. And then in many instances, I believe JPEG is a good example. No, there was another JPEG where the maintainer of that filter, if they then use these CD values, actually tell you exactly what these CD values are. Now I can't find it. I saw an example earlier. Maybe I shouldn't have clicked on that. I think it's in the table itself. I think the JPEG filter is an example. Here's a JPEG and here's another JPEG. Which JPEG was it? Was it this one? No. That's embarrassing. Let's see. Was it this JPEG or this JPEG? No. Oh, here, it was this one. So here's an example of, this is the JPEG filter with ID, filter ID 32019. And here are the CD values that are specific for that filter. So that should be your first port of call, so to speak. And then, yeah, if you want to use these CD values with H5 repack, for example, H5 repack, and I think most of the command line utilities support user-defined filters in conjunction with the HDF plugin path, for example, environment variable. And here's how you would specify these CD values. Maybe, we have Dana here. I don't know, in version in HDF 2.0, I think the filter pipeline or the sort of, yeah, the extension interface, let's call it that, of the filter pipeline is also, I think, on the table. Any improvements we can make to that for users to make it more intuitive, easier to use, and all the rest of it. Maybe Dana can say a few more words. So right now it is what it is. It is a little obscure, but it's ultimately the responsibility of the filter owner. But yeah, starting with the filter registry, I think that's the best place to start.
Yeah, I don't have any specific things in mind right now. I mean, I haven't had time to carefully sit down and look at that for future improvements. But yeah, the filter interface is frequently a cause of pain for users, particularly with respect to memory and its reallocation. So we want to make that easier to use.
And it's your corner anyway. Anything else you would like to share with people, give an update on? And
no, Mark Miller had a big set of things that he listed on there. I saw that he had posted that. Again, I haven't had time to look at that. I was trying to get HDF5 113.2 out the door the past couple days, but he had a really long, good post on there. So.
And how is 113.2 coming along?
It's just about ready for release. We're just fixing, there's like one small test failure in the subfiling stuff that we have to address. There's a PR up for it. I just haven't had time to review it today because I'm in meetings, but that should get fixed today and we should create the branch in the next day or so.
Okay.
And then it'll be released, 2 weeks after that.
Yeah, probably there won't be a 113.2 beta release.
No, I think we're just going to send it. I mean, they are essentially beta releases. I mean, you can view every single 113 release as a release candidate for 114.
Okay. Anything else? Otherwise, we'll just move on.
No, nothing else.
Okay. So maybe I'm going to pause. I have something prepared for tips and tricks, but are there any questions in the meantime? No? Okay. Then, okay, so today then for our tips and tricks, that's maybe a variation on a theme that we covered not in not too distant a past. We talked about data conversion, data type conversion, that is. And interestingly enough, the user who originally raised that question asked, the example that we provided back then was we converted a bit field to a compound type that had 2 integer components. And then the user came back and said, that's fine, that works great. But then they were asking, well, what in this particular case, the byte size of an individual element was the same. So we chose, if I remember correctly, a 32-bit bit field and a compound that had 2 16-bit unsigned integer fields. So in both cases, the size is 4 bytes. And they said, great, but what if the size of the source and destination are different. Can I do, first question, can I do a data type transformation under those circumstances? And if yes, how do I do it? And the answer is yes, you can, of course. And so I just prepared a little example for that. And if you wish, the trick is basically you use what's called a conversion buffer. And so I've modified the original example a little bit. So what we are going to do is, for argument's sake, we are going to convert that same 32-bit bit field into a 64-bit unsigned integer. So we basically grow in size. And that's what also that user was interested in, how if my destination element type is larger from a byte count perspective than my source type. So in this case, maybe I should first talk about the callback function and then sort of talk about the main function, although the main function is maybe easier to grasp. But so if you think about it, we have a 32-bit bit field and we want to convert that into a 64-bit unsigned integer. And yeah, that's kind of not that difficult because in a way, well, we have 4 of the 8 bytes that we need, and we just have to sort of shift that, slot that into place. And it's I made it also extra easy. We don't have to worry about the sign position and things like that. So if you had a sign and so forth, then things would be slightly more complicated, but the idea is the same. So with that in mind, of course, yeah, we have our conversion function that does the actual conversion. Again, in this case, the background buffer is typically relevant only for compound types. So in this case, there is no background buffer. It's really just the conversion buffer. And so in terms of the logic, this callback function will receive a buffer in which we have sort of a certain number of elements who are 32-bit bit fields. And however, the size of that buffer will be such that we can also fit the converted elements, which are twice as large in this case, into the same buffer. So for argument's sake, let's say I get a buffer that, according to the input arguments, contains 10 32-bit bit fields. Then you might say, okay, 32-bit bit, that's 4 bytes. So is that buffer 40 bytes? No, it's actually, since our destination is unsigned 64, which is 8 bytes, it's actually not 40 bytes, but the total buffer size is going to be actually 80. So the buffer that we are receiving has already the right size. All we have to do is to take the 32-bit bit fields that occupy, so to speak, the beginning of that buffer and basically slot them into the right places into this bigger buffer. That's all what this conversion function has to do. So, and it's actually very straightforward. Again, this is highly simplified. We are not worrying about any kind of initialization that we would have to do for this conversion. Likewise, we have no custom things that we need to free. So there's nothing to do here. So it's really just if that callback tells us, okay, let's convert some data, what we have to do is we have to basically look at that buffer from 2 different angles, so to speak, or 2 different perspectives. One is sort of the 32-bit bit field or unsigned 32-bit integer perspective, or as we have to look at this as an array of unsigned 64-bit integers. And yeah, the conversion happens in place. And of course, the only thing that we could do wrong here would be if we tried to convert that first element first, it would have to actually grow a little bit because it currently or initially occupies 4 bytes, but we have to make that 8 bytes. But if we did that first, we would actually be overriding the 4 bytes, our next 32-bit bit field. So we can't do that. which means we have to actually do this backwards. So if we have, let's say, 10, for argument's sake, 32-bit bit fields, we actually have to start with the last bit field and sort of shift that up and slot that into the right place, and then sort of, yeah, really work our way down to the beginning in order to not overwrite any of the existing data. That's why this loop here is backwards. So we start, this callback tells us how many elements we are being asked to convert. So we start at n elements, I greater than 0. So we are counting down and we are decrementing our loop index. And then, yeah, we basically cast that 32-bit integer, that 32-bit unsigned integer or bit field, and basically assign it, cast it to a 64-bit and assign it. So the conversion function intentionally is very simple in this case, but then again, you can make it as complex as the source and destination types require. So this conversion function, this is our conversion functions going from a 32-bit bit field to a 64-bit unsigned integer. And now, how do we exercise this function? And what about, I said something here about a conversion buffer. Where is that conversion buffer? Well, okay, so let's look at our main function. So we have sort of our, in memory, our source type, which is our 32-bit bit field type. And then in the file, we are going to use a unsigned 64-bit little endian. And then we register, as last time, we just register our conversion function as a soft conversion. And symbolically, I'm going to call it B32 to U64. And here's my function pointer, and that's all good. And then again, I use the same example. I create a 32-bit, a 32-element set of bit fields and just initialize it with powers of 2, because that makes it easier to check what's going on. And then, yeah, we just create an HDF5 file and then create our data set of integers. In this case, uint might be a little misleading, but remember, uint is really 64-bit integers here. So we create a data set whose element type are 64-bit integers. And now we are coming to this buffer. We provide that buffer as part of a data set transfer property list. If you remember, both H5D read and H5D write, the previous to last argument in both cases is what's called a data set transfer property list. And one of the properties that we can set in such a data set transfer property list is to provide a conversion and a background buffer. In this case, the background buffer is not necessary and irrelevant. However, and the library actually gives us two options. Either, and I mentioned that here in a comment, either we can rely on the library and say, okay, I would like to convert up to this many elements at a time, but I don't want to get involved into allocating any kind of buffers, be it conversion buffers or background buffers or something like that. So in that case, you would provide only the size in bytes of the maximum amount of elements that you are willing to convert in one, let's call it in one step, so to speak, because imagine you have a very large data set for which you want to do that conversion. You may not have enough memory to sort of create that second conversion buffer of that whole thing. So you can really do what's called strip mining. So you can have like a sliding window. We just talked about sliding windows. You can have a conversion window that you are sliding over that in-memory buffer and do the conversion sort of in windows, in increments, in strips like that. And so in this case, I'm going to say, okay, I'm going to go with 48 bytes. That would give me, this is in reference to the source type, which is 32-bit bit fields in this case. So I could convert, which is 4 bytes. So I could convert 6 elements at a time. And if I specify for these buffers here, null in both cases, the HDF5 library will actually dynamically allocate these buffers for me, these buffers that then appear in my callback. And however, you can rightly argue that there is certainly a little bit of overhead attached to allocating and freeing and allocating and freeing these buffers. So that's why you can provide those buffers right out of the box. So that's what I'm doing here. I know that I want to do 6 elements at a time. They are 8 bytes each, so I need a total of 48. So I'm just allocating a 48-byte conversion buffer, so to speak, and I provide that as the first argument here, and there is no background buffer needed here, so I can just make that null. But I know that the library is not going to try to allocate that background buffer because it sees that that's not really necessary for this type of conversion. And that's it. And then I just call H5D write, and you see here I provide that instead of H5P default, I provide that data set transfer property list as that argument. And then, yeah, it will just create an HDF5 file that has that one data set of integers in there, in this case, unsigned 64-bit integers. And yeah, we have written a data set, so to speak, in memory, whose elements are 4 bytes to a data set through a data type conversion to a data set of elements whose byte size is 8 bytes. And that's it. And that's really all there is. So likewise, the other direction, if you want to go from a larger to a smaller, you can do that. Again, you have total control through the callback, through these buffers. You can accommodate all kinds of needs. Elena. Mm-hmm.
Yes, sorry, my camera stopped working. So this is the question. There was also some discussion on Slack, and I was kind of confused. Even I probably should know. What happened in the case when a really big buffer and a conversion is done? Does library allocate if I pass null the size of the same buffer? Probably not, or it writes in small portions. What actually goes to H5D write call? How H5D write works?
Oh, H5D write, yeah, it works very simple. So I think the so your question is actually, so from this setting, it's clear that my callback here will be invoked at most or for up to 6 elements at a time.
Right.
We agree there. So, but I guess your question is, how does that data actually eventually get written back to that data set?
Right, are we writing by 6 numbers? Right.
I guess that's a good question. I don't know the answer. I would think
Quincy is here. Maybe he can answer.
Yeah.
Gerd,
it probably. Quincy?
The buffer size will ultimately restrict the amount of data that the dataset write has available. And so it will limit, in this case, the IO to 6 bytes, well, 6 elements at a time. Because it has really no other place to put data. The user was specific and they said, use a buffer of this size, and that's the upper bound.
Right. Yeah. This makes for big writes, it makes it, especially when conversion is going on, very inefficient because you're writing by a much smaller amount, depending on how much memory.
The general intention of the buffer size was to specify a larger buffer than the library's default, not necessarily a smaller one.
Right. And as far as I know, the library's default is 1 megabyte. And I think there's also a difference between if the data set is chunked and you have your chunk cache right, as long as the conversions fall onto the same chunk, which sits in a chunk cache, of course, it's not going to write anything, only when that chunk gets evicted or flushed or something like that.
Yes,
Yeah,
that's
but,
right.
right, but data conversion happens before, right, when it still sits in a chunk cache. So we need to be careful explaining. It really depends on the application resources, how much write memory it has, because it really can start consuming a lot. And
yeah, but you have control. So yeah, it's really, of course, yeah, if you can, for example, in the case of a chunk data set, if you can align it with the chunk size or the nominal chunk size, if there's compression, then that's really just a nominal size. If you can align it with that, but yeah, if it's contiguous, then yeah, you want to be careful. And it's a trade-off between, oh yeah, currency has to drop. If it's a contiguous data set, then it's a trade-off between, yeah, you have more write calls or read calls depending which direction you go, and yeah, you want to make that buffer as large as you can afford.
Let me ask, this is another thing. So how it will work if I have chunk that conversion, it happens when chunk goes from chunk cache to user buffer, right?
I would think so.
What would happen if my conversion when it goes to chunk cache is bigger than it has to be evicted immediately? How that conversion will work? So it will extend it, convert everything, and then
no. I mean the let's call it the nominal element size of the chunk and the chunk cache is of the destination type. So if your destination type is smaller, the chunk will be smaller.
Right.
If you're, so that's already correctly sized.
Right. Sorry.
Yeah, no, that's okay. So I thought this is I mean, I think it's a double-edged sword. On the one hand, this illustrates a powerful capability, but as most powerful capabilities, it comes with a sort of with a disclaimer or with an asterisk that says, well, number one, your mileage will vary and use with caution. And but in this case, the use case is actually very legitimate. Again, just for context, in like experimental setups where people oftentimes they just read bit fields. That's all they get from their devices, and then they have to convert that into engineering units and so forth. And yes, you might want to save the bit fields for archival purposes, but then when you hand that data to users, you want to also hand them a data type conversion function, so that when they read the data set, you can say, okay, read this as a velocity, as a floating point number, or as an integer, or as a compound with multiple components. And so the legitimacy of the use case is there clearly. But then, there are consequences, or there are implications for the convenience of being able to store something in some form, but then pretending to be something else, so to speak. Okay, good. Sorry, we are out of time. Please come back next time. If you have any questions, leave them in the Google Doc so I can prepare. And yeah, thanks for coming, and see you next time.
Thanks.
Bye.
Bye-bye. Thank you.
Thanks.